Jupiter's mysterious plasma waves. A NASA Juno breakthrough. Prepare to have your mind blown. Jupiter, the gas giant, is broadcasting mysterious waves that have left astronomers scratching their heads. NASA's Juno spacecraft has picked up an entirely new kind of plasma wave hovering above Jupiter's north pole, revealing an unprecedented interaction between different charged particles in the planet's magnetosphere. This discovery, published in Physical Review Letters, is one of the strangest plasma behaviors ever witnessed in our solar system. It could revolutionize our understanding of Jupiter's intense auroras and the magnetic environments of other planets and distant stars. But here's where it gets controversial. This discovery might also challenge our current theories about how plasma behaves in space. So, let's dive in and explore this cosmic enigma. Jupiter's magnetic field, the maestro of synchronized plasma waves. Since 2016, Juno has been circling Jupiter, collecting detailed information about its atmosphere, magnetic field, and polar regions. In this latest revelation, scientists from the University of Minnesota, the University of Iowa, and the Southwest Research Institute stumbled upon something extraordinary. They found Alfvén waves and Langmuir waves, two distinct types of plasma oscillations, moving in perfect harmony within Jupiter's highly magnetized, low-density polar regions. Typically, these waves operate independently. Alfvén waves are influenced by the movement of charged atoms, while Langmuir waves are driven by electron oscillations. Because electrons are much lighter than ions, their wave frequencies usually differ significantly. But near Jupiter's poles, these waves were oscillating together, creating a plasma behavior never before observed in space. Imagine trying to synchronize a flock of birds with a school of fish. It's nearly impossible, right? But that's exactly what's happening in Jupiter's magnetic field. The planet's intense magnetic field forces different plasma populations to interact in ways we never imagined. As planetary scientist John Leif Jorgensen told New Scientist, the observed plasma properties are really unusual, not found before and elsewhere in our solar system. And this is the part most people miss. This unique behavior could be the key to understanding not just Jupiter's auroras, but also the magnetic environments of other planets and even distant stars. A deep dive into Jupiter's auroras and their cosmic counterparts. Unlike Earth, where auroras are mainly caused by solar storms, Jupiter's auroras can be triggered solely by its colossal magnetic field. The resulting emissions are hundreds of times more energetic than those in Earth's atmosphere, creating breathtaking displays of ultraviolet light above the poles. These new plasma wave discoveries offer a deeper look into how those auroras work and why they're so powerful. The study suggests that the unique wave interaction could be linked to the dynamics of Jupiter's auroral regions, which serve as a natural laboratory for studying planetary magnetospheres in extreme environments. But here's a thought-provoking question. Could these plasma conditions exist elsewhere in the universe? Scientists believe they might. It is possible that they apply in polar regions of the other giant planets, and potentially in strongly magnetized exoplanets or stars. The team wrote in their paper, "This opens up exciting research opportunities beyond our solar system." The legacy of Juno and future expeditions to Jupiter. NASA initially planned to end Juno's mission in 2017 by sending the spacecraft into Jupiter's atmosphere to prevent contamination of its moons. However, mission planners extended its lifetime after determining it posed no threat to the Jovian system. Since then, Juno has continued to send back invaluable data from its evolving orbit. But all good things must come to an end. Scientists estimate that by September this year, Juno's orbit will degrade enough for the planet's atmosphere to consume it. Yet, the mission's legacy will live on as researchers continue to analyze its vast datasets. NASA's exploration of the Jovian system is far from over. The Europa Clipper, scheduled to arrive at Jupiter's moon Europa in 2030, will be the next big step in the search for potentially habitable environments elsewhere in the solar system. As Scott Bolton, principal investigator of the Juno mission, eloquently put it, Jupiter is the Rosetta Stone of our solar system. Juno is going there as our emissary, to interpret what Jupiter has to say. So what do you think? Is Jupiter trying to communicate with us through these mysterious waves? Or is there more to this cosmic puzzle than meets the eye? Share your thoughts in the comments below. discovering a new type of plasma wave near Jupiter's poles. Prepare to rethink what you know about Jupiter, because scientists have just uncovered a phenomenon so unexpected, it's challenging our understanding of planetary physics. Imagine a new kind of plasma wave swirling above Jupiter's North Pole, a discovery that opens up fresh mysteries about the universe's most massive planet. But here's where it gets particularly intriguing. This new plasma wave doesn't fit any pattern we've ever seen in our solar system. What might this mean for how we study exoplanets or even hunt for alien life? Let's dive in. Since NASA's Juno spacecraft settled into Jupiter's orbit back in 2016, it's been peeling away the layers of the gas giant's secrets. With each orbit, Juno's sophisticated instruments have revealed everything from breathtaking images of Jupiter's chaotic weather systems to new insights into its intimidating magnetic field. The latest breakthrough comes from a team of scientists who have, for the first time ever, detected a brand new type of plasma wave shimmering near Jupiter's North Pole. The details, published in the journal Physical Review Letters, describe a phenomenon occurring within Jupiter's magnetosphere, a vast magnetic cocoon that shields the planet from cosmic radiation. Essentially, Jupiter's immense magnetic power is causing two fundamentally different types of plasma, charged particles that make up much of the universe, to ripple together in a perfectly synchronized dance. It's an occurrence never before observed, and it raises eyebrows. Could such a unique interaction impact weather on Jupiter, or even help us understand the atmospheres of distant worlds? To help clarify for newcomers, plasma is an energized, electrically charged state of matter. It's everywhere in space, inside stars, in the solar wind, and, as it turns out, in Jupiter's turbulent clouds. When scientists looked more closely at the plasma above Jupiter's poles, they discovered an unusual oscillation linking Alfvén waves, ripple effects caused by the movement of the plasma's heavier, charged atoms, and Langmuir waves, generated by the swift motion of much lighter electrons. Usually, these waves move at separate speeds, but on Jupiter, they mysteriously vibrate together. Here's the part that most people miss. This discovery isn't just a footnote in an astronomy journal. It suggests that Jupiter is home to plasma behaviors that defy the rules we thought applied everywhere in the solar system. As planetary scientist John Leif Jorgensen, who wasn't part of the study, noted, such plasma characteristics have never been seen elsewhere. Why is Jupiter so special? Is there a deeper mechanism we haven't yet grasped? Now, if you're picturing Earth's northern and southern lights, those ethereal auroras that paint the sky during solar storms, think again. Jupiter's auroras are hundreds of times more energetic and can be triggered not just by solar wind, but by the planet's own magnetic might. These insights could be a roadmap for future missions seeking signs of life beyond Earth. If giant planets or exoplanets have similar plasma behavior, what might their auroras or environments be like? The scientists speculate in their paper that conditions like these, while unprecedented on Earth, might actually exist at the poles of other gas giants or even around magnetically intense stars and exoplanets, raising the possibility that we're only just beginning to grasp the variety of plasma phenomena in the cosmos. Scott Bolton, Juno's principal investigator, once called Jupiter the Rosetta Stone of our solar system, suggesting that unlocking its secrets could help us interpret planetary mysteries everywhere. And the mission itself wasn't supposed to last this long. Original plans called for Juno to plunge into Jupiter long ago to avoid contaminating its moons, in line with NASA's strict protection protocols. But new data confirmed Juno posed no risk, buying more time for this spectacular science. Fast forward to now, Juno is still orbiting, but scientists anticipate that by September this year, its journey will naturally end as Jupiter's gravity tugs it inexorably toward its atmospheric depths. Still, this isn't the end for Jupiter exploration. The highly anticipated Europa Clipper mission is set to reach Jupiter's moon Europa in 2030, aiming to unlock even more secrets. And here's a provocative question for you. Does the discovery of such mysterious plasma behavior suggest that the rules of physics could be more flexible than we thought, especially in extreme environments? What implications might this have for our search for life or understanding of other worlds? Do you agree with the scientists' interpretation, or do you see a different angle? Share your thoughts or challenge the findings. After all, real scientific progress thrives on spirited debate. Jupiter's plasma mystery. NASA Juno discovers hybrid waves that break physics rules. Prepare to have your understanding of space physics turned upside down. NASA's Juno spacecraft has uncovered a bizarre new type of plasma wave swirling above Jupiter's North Pole. One that could force scientists to rethink the very foundations of plasma physics. And this is the part most people miss. What Juno found doesn't just challenge our models of Jupiter, but could rewrite the rules for how we understand magnetic fields across the universe. Let's break down what's happening. Since 2016, Juno has been orbiting Jupiter, sending back a treasure trove of data and images about the giant planet, its moons, and its iconic rings. But as Juno's mission progressed, its path shifted, giving scientists a rare, up-close look at Jupiter's mysterious North Pole, a region few spacecraft have ever explored in detail. Jupiter's magnetosphere is a true cosmic powerhouse. Imagine a gigantic bubble carved out of the solar wind by Jupiter's immense magnetic field. This bubble, or magnetosphere, is so vast it nearly reaches Saturn's orbit and stretches about 7 million kilometers toward the Sun. It's the largest magnetosphere in our solar system, making it a prime laboratory for astronomers eager to unlock the secrets of magnetic fields and plasma behavior. But here's where it gets controversial. Juno's instruments detected plasma waves in Jupiter's magnetosphere that simply don't fit with what scientists have long believed about how charged particles behave in such environments. The findings, led by Robert Lysak from the University of Minnesota, describe plasma waves that defy the standard models, leaving experts scratching their heads and questioning decades of assumptions. During its close passes over Jupiter's North Pole, Juno found regions in the magnetosphere with extremely low electron densities. In these zones, where magnetic fields can reach up to 20 Gauss, that's 2 millitesla for the technically inclined, Juno observed something truly odd. The plasma frequencies were much lower than the ion gyro frequency, which is the opposite of what's typically seen in plasma physics. Normally, Alfvén waves, which are linked to ion movements, and Langmuir waves, associated with electron oscillations, behave in very distinct ways. But in Jupiter's polar magnetosphere, Juno detected a strange hybrid, Alfvén waves that started to act like Langmuir waves. This new phenomenon, now dubbed the Alfvén and Langmuir mode, blurs the lines between two well-established types of plasma waves. And this is the part that could spark debate. If these hybrid waves exist at Jupiter, could similar plasma behaviors be happening around other planets, or even magnetized stars and exoplanets? If so, our current models for interpreting cosmic magnetic fields might need a major overhaul. The research team suggests that these hybrid waves may be triggered by powerful electron beams shooting upward, with energies ranging from 1 keV to 2 MeV. Interestingly, Juno has observed such energetic electron beams before, especially during earlier flybys of Jupiter's polar regions. The implications are huge. If this new plasma regime is real, it could open the door to breakthroughs in how we model not just Jupiter's magnetosphere, but also the magnetic environments of other worlds. Imagine being able to better predict space weather around distant exoplanets, or understanding the magnetic fields of stars light years away, all thanks to a discovery made above Jupiter's North Pole. The full details of this groundbreaking research are published in the July 16, 2025 issue of Physical Review Letters, in a paper titled New Plasma Regime in Jupiter's Auroral Zones, by R. L. Lysak and colleagues. But here's a question for you. Do you think this discovery truly signals a paradigm shift in plasma physics? Or is it just a quirky exception unique to Jupiter? Could our textbooks soon be out of date? Or will further research prove these waves are a rare cosmic oddity? Share your thoughts. Do you agree with the researchers? Or do you see another explanation? Let's get the debate started in the comments below.